Hello, this is Functional Analysis, and we have just started Chapter 4, which will turn out to be an introductory chapter to the spectral theory of bounded linear operators. However, before we get to that point, we have to prepare some material, and we started by first introducing three types of convergence on the vector space of bounded linear transformations. After that, we discussed the adjoint for a given bounded linear transformation on a Hilbert space, and now currently we are looking at more specialized classes of operators. So we discussed what are normal operators, self-adjoint operators, and now here we will be dealing with a result for the so-called unitary linear transformations. We have this little lemma here in front of us. This will be a helper later on. So it states if a linear transformation obeys this u star u is the identity on the first space, then this happens if and only if it is an isometry, namely ux in the second norm is equal to the norm of x in the first norm for all points x in the first Hilbert space. Okay. Now it turns out such a u is unitary, so you remember for u to be unitary, besides this equality here with the identity in the first space, you also need the other one where you compose u with u star and you get the identity in the second space. Right, so that's what it means to be unitary. And it says here such a u is unitary if and only if it is surjective. Alright, so this will be a little helper, because once we have this helper, we don't need to check anymore both of these equalities, u star u is identity and u star is identity. One will be enough, plus the fact that we're dealing with a surjective linear transformation. Alright, so let's do it. Proof. Let me first write a statement and then explain it to you. So by polarization, so remember the polarization identity, we actually proved it in the exercises, and it was stated in the manuscript in the lecture notes earlier on. So there's two of them. There's one if the underlying field is the complex number field. That's the one, the more complicated one that I will use here. Let's put the 4 on the left, otherwise we have to write a lot of quarters there. So it is this one, minus x minus y squared plus I x, and then just y replaced by iy. Okay, so this is the one when you are on the complex number field. If you are on the real number field, then you just drop these guys here that are under the green bracket. All right, then that would be your polarization identity. All right, now using this, I claim we obtain that u star u is the identity on H1 if and only if x u star ux, that's inner product in the first space, is equal to the norm squared of x for all x in H1. So why is this true? Well, first let's think here. There's an easy direction, right? So if you assume that u star u is the identity, well then here in this factor this would be the identity, and then you have just you're just writing the fact that the norm squared is the inner product of the vector with itself, right? So clearly this guy here is true, that direction. That doesn't need much thought. Now the other direction, that's where you need the polarization. So let's remove this. So how would you do this up there? Well, you assume the right hand side, so that the norm of x squared is equal to this inner product. So now, since this is valid for all points, for all vectors in your Hilbert space, you can successively apply it for these 4 guys up here, right? So I will write it out for one of them. So instead of x plus y squared, now I use my assumption, so this will be x plus y, and then u star u x plus y. All right, and you have 3 more of those for the other guys with x minus y, x plus iy, and x minus iy. All right, but the logic for all 4 of them is the same, so I will only explain it here for one. Now what you do is you use the definition of the adjoint, that was our yellow box. So you move the u to the first vector, you get this, ux plus y. And now you can use linearity of u, right? U is a linear transformation, so that allows you to write this as, well, ux plus uy in the first vector and the same in the second vector. Yeah, but then what you have here is ux plus uy norm squared. Okay, so and this you do for all four norms here on the right hand side, and then what it tells you is that so all that you have achieved now is you've replaced sort of x by this x tilde and y by this y tilde, right? So by the polarization identity, this would give you on the left now 4 times ux with uy by polarization, but you started with 4 times x comma y, right? So and these two guys have to be the same for any points x, y in the Hilbert space, right? So but that implies immediately, you can for instance put this u again over here, so you have the u star u. This immediately implies the left hand side that u star u has to be the identity. Okay, so that works with polarization. All right, good. So that we have established this, let's continue, but let's erase this yellow stuff here again. But x u star ux in the first space is by definition of the adjoint ux in the second space, which is equal to ux2 squared, right? So the first equivalence follows. So the first equivalence follows. Right, I convinced myself that u star u equal to the identity is first equivalent to this thing here underlined, and then here the left hand side is equivalent to this, and that's precisely what's written up there in the statement. U star u is identity if and only if u is an isometry, and that's what I just proved. Okay, good. So we have this finally, and now the rest is easy. Any isometry is injective. That we have already used multiple times before. Any isometry is injective. If it is also surjective, then it has an inverse. Remember this kind of argument. Now you can either cite the inverse mapping theorem because you're over a Hilbert space here, or you use the same argument that we did in that section on duals and double duals before we had the inverse mapping theorem, because we know now it's bijective, and the isometry, that equation immediately lets you conclude that the inverse has to be bounded, right? So either way you get to the same conclusion. Then it has an inverse S L H2 H1, and so SU is equal to identity on H1, and US is equal to identity H2. Of course, this S is just U to the power -1, but I don't use that notation because I have to show now that S is equal to the adjoint, right? That's why I prefer S, okay? But then U star, so a little bit of algebra. U star is the same as if I multiply by the identity, which is US. Now that composition here, or multiplication, is associative, so I can put the brackets as I like. But then remember that product here, U star U, in the first part we had this equivalence, right? So we are currently dealing with a such a U, so one that is an isometry and which is also surjective, so the isometry is equivalent to U star U being the identity, right? So this is by the first part just equal to S. And there you have it, right? That's what I said. I have to show that the inverse S is actually the adjoint, and there it is, all right? So let's summarize it. So U star is equal to the identity on H2, and right? That's why we now have U star U is identity on H1, and U star is identity on H2, hence by definition U is unitary. Okay. Conversely, if U star is also IH2, that is U unitary, then I just have to show that U is surjective. Then for any x in H2, we have x is equal to u star x, right? And so x in the range of u, right? Here's the corresponding element, this one here, that shows that x is in the range of u. Okay, this concludes the proof. This concludes the proof. Okay, very nice. This is a little helper. We had one helper before that for self-adjoint operators, and now we have this one here for the unitary linear transformations. Next one that will now quickly get us to the projections, which are very useful. So first let T be bounded linear transformation between two Hilbert spaces. Then remember the orthogonal complement. Turns out we have the following relation between the range and the kernel of T and its adjoint using the orthogonal complement. So the kernel of the adjoint is just the orthogonal complement of the range, and the kernel of the ordinary one is just the orthogonal complement of the range of the adjoint. Okay. Once you have one, the other one you get for free. So suppose you manage to prove that green underlined thing. How do you get here? Well, since this is true for any t, you just replace t by t star, using that the adjoint of the adjoint is the original thing. This was one of the key properties of the adjoint, which sets it very much apart from the dual transformation. All right? So it will be sufficient to just prove, say, the left one here. Okay, so let's do this. These are subspace equalities. They are probably also known from linear algebra, because the proof that we do now does not use any assumption on the dimension whatsoever. So usually one also does this in linear algebra. Indeed, the proof is a one-line chain of equivalences for an arbitrary vector in the second space. So t star x equal to 0. This happens precisely when, well, 0 is y t star x. So this is in the first space for all y in H1, right? Because from left to right here, that's clear, because you take inner product with the 0 vector, that will be 0. And from right to left, well, if y inner product t star x is always 0 for any y, then you just replace y by t star x and conclude that t star x is equal to 0. Okay, and now here you just use again, well, soon I will be stopping indicating that yellow box. So this is just t y x in the second space, right? So what you have here is that t star x equal to 0 if and only if tyx equal to 0 for any y in H1. Let's move this a little bit to the right. Yeah, but now if you read the one on the far right, that precisely says that, remember, t of y is an element in the range, right? So that's precisely saying that x is orthogonal to everything in the range of t. In other words, x is in the orthogonal complement of the range. And that's it, right? So you have now the left-hand side. This is precisely what happens when you're in the kernel of the adjoint, and the right-hand side, that is when you are in the orthogonal complement of the range. And that's that green underlined equation up there. All right, so that's it. Second claim, as I already explained up here in green, you get by replacing t by the its adjoint. Good. Before we prepare the projection now, so maybe here one comment. So by the projection lemma, this was back in chapter 2, for a given bounded linear operator on a Hilbert space, for given t, any vector x in H admits I claim a unique representation of the following form: x is equal to y plus z, where y is where and z is somewhere else. So what I'm going to do is, in the projection lemma, the statement was, if you're in a Hilbert space and you have a closed subspace, then that will decompose the whole space into that closed subspace and the orthogonal complement thereof, right? So what I'm going to do now is, here with my T, I will start with a closed subspace, which is the kernel of the adjoint. You could also take the kernel of T itself, it doesn't matter. However, the way I write it now, I will use it later. That's why I do it. So we apply the projection lemma. This is our closed subspace. Kernels are always closed of bounded linear transformations. And we will take the kernel of the adjoint. Right? And then the projection lemma says that y is in there and z is then in the orthogonal complement. Yeah, but that we just figured out what that is. So the orthogonal complement of the kernel of the adjoint is the orthogonal complement of the orthogonal complement of the range. Right? So this will be in the orthogonal complement of the orthogonal complement, and that was a little result listed in the lecture notes, but you proved it in the exercises. That's the closure of the range. All right, and this thing we will use later on when we discuss spectral theory. That's why I wanted to mention it right now. In turn, if we use the language of complementary subspaces, which we discussed in chapter 3 right before we proved the closed graph theorem, this just says the following thing: given a Hilbert space H and T bounded linear operator, then kernel of the adjoint, kernel T star, and the closure of the range are complementary subspaces. Right, so remember the notion of complementary subspaces, just meaning that any vector you can write as a sum of, well, one part belonging in the first one and the other one in the complementary one, and the complementary and the original one, they intersect in the zero vector. And that's precisely what the projection lemma gives us here. Okay, good. So now, I already said at the end of the last video, so now we will clarify why this projection lemma is called projection lemma. So we will now quickly define, discuss a very important class of bounded linear operators. Those are operators, not linear transformations. And this we can do on a general non-linear space, normed linear space. We say it is called a projection if you apply P twice, so you compose P with itself, then you're not going to gain any new information because it's just going to be P itself. If in addition you can make sense of the adjoint of a projection, so that means you are in a Hilbert space, is a Hilbert space, and P is self-adjoint, then P is called an orthogonal projection. Good. So that's the definition, and now it turns out using pure algebra has nothing to do with analysis, just algebra and this definition. There are acute properties around, so let PLX be a projection on a normed linear space X. Then, three properties. Number one, if you look at Q, which is identity minus P, then first off, this is again bounded linear operator, that's clear. Moreover, is also a projection. And it commutes with P and the composition is equal to 0. Number 2, the range of P is equal to the kernel of Q, and that in particular tells you that the range of any projection is closed because it's equal to a kernel of a bounded linear operator, and kernels are closed, right? So that again identifies projections as something sort of remarkable, because having a closed range doesn't appear that often. For instance, it appeared in the canonical map when we were discussing the bidual, and that thing was of course also important. Okay. And we have a sort of complementary one. The range of Q is equal to the kernel of P. Let me write this out. Range of any projection is a closed subspace, right? And then number 3, and that now explains why it is called projection lemma earlier on. We will discuss it further after I have proven these 3 properties. The kernel and range are complementary subspaces of X. Alright, so maybe one more time I'll write what it means. So that means X is kernel P plus range P, and they intersect only in the 0 vector. Right, so they complement one another to get the full thing. All right, that's it. So now we have to prove this, and this is really just algebra, just playing around with the definition. Well, if you have a bounded linear operator P, and you look at identity minus P, that's still going to be bounded linear operator. So that's clear. And since now we have to compute Q squared, so this is 1 minus P, 1 minus P. Naja, and then you multiply this out, 1 minus P plus P squared. But remember, the key property of the projection is P squared is equal to P. So one of these guys here goes out, say the third and the fourth. So this is 1 minus P, which is equal to Q. Right? So Q indeed is a projection. Also, does it commute with P? Well, PQ is P, 1 minus P is P minus P squared. This is again P minus P, well, surely is equal to 0, is the same as P squared minus P, is the same as, well, which way do I want it now? I want 1 minus P. Yeah. What I wrote is correct, but I want that square over here. Yeah, so that's fine, right? So, and this is QP, right? And that's what I claim. P and Q commute and they're equal to 0. Okay, fine. Moving ahead, so number 1 is established. Moving ahead, let's see how much time. Oh yeah, maybe we can do 2. Moving ahead, we have to show that, say, range of P is equal to kernel of Q. Let's write it here in yellow, so that is the goal. Right, so this is a subspace equality, so you show that one is sitting inside the other and vice versa. Moving ahead, which one do I do first here? Y in the range of P. Okay, so that just means by the definition of the range that there is some x such that P of x is equal to y. Okay, and thus if you apply Q of y, well, then you have QP. Then again it's associative, so you can put the bracket like this, but you already know from the first property that Q times P, that composition is equal to 0, so this is just 0. And that shows that y is in the kernel of Q. So y in the kernel of Q. All right. The other direction is not much harder. Conversely, if x is in the kernel of Q, then, okay, So Q is 1 minus P, so then I have 1 minus Px is equal to 0, which is just x is equal to P of x, and that tells me that x is in the range of P, right? Because here's your element that maps it to that x itself, right? So that means we have the yellow stuff. Now, how do you get the other one where you have range of Q is equal to kernel of P? Well, by formally, remember this is the one in yellow that we just proved is valid for any projection P, so it's in particular valid for the projection Q, which is 1 minus P, right? So by formally replacing P with 1 minus P is equal to Q, we then also find good question. So then you have range, so P is replaced by 1 minus P, so that you have the range of Q, and then you have here kernel 1 minus, and now P is replaced by 1 minus P. Okay, so this is then the kernel of P. Right, so range of Q is equal to the kernel of P, which is the second one. Good. I think I will stop here. What now remains to be seen is the statement about the complementary subspaces. That's also not hard. And then once we have that, then we will clarify why that projection lemma was called projection lemma, one more result, and then we will begin with the spectral theory, which is lots of fun. I'll see you soon.